record button here. As opposed to utility scale wind. So again, if you drive out west from Chicagoland, you're going to start to see lots of windmills further out in Illinois, downstate Illinois. Certainly, we drive now to Denver, and once we get into central Iowa, there are lots and lots of windmills up. So something is going on here. Well, what's going on is that scale matters in this case, right? So the windmills that you see along the road, it's hard to really judge how big they are, but you're talking about something that's your swept area is 130 meters, right? A couple hundred feet in diameter and height. So this is the scale that firms are building these large windmills on. Again, the deal here is the height, being in a rural area with less obstructions and good wind resources, and the height gets that rotor up to where the wind is stronger. So, that's what's going on with this technology. Again, I need to update my slides here, but you can see where we have the installed wind capacity. Surprisingly, at least for me, right, I think of Texas as a deep red state, but Texas actually leads the country in installed wind capacity. Right? If you remember that resource map, you saw a lot of resource in the Texas panhandle here. So again, up to the Plain States, fairly large amount of installed wind capacity, and pretty decent amount in Illinois as well. I think that's for 4,000 megawatts or 4 gigawatts of installed capacity, but 20 gigawatts of installed capacity in Texas. So again, utility scale wind technology, there continue to be improvements in this technology in materials and aerodynamics that allow for longer blades and taller hub heights and more output per machine, right? More output per machine makes it less expensive to install. Installed costs are dropping because we're putting more machine on that same foundation. And I'm going to turn my video off here again. I think my computer's acting up. Right as we scale up the machines, the fixed costs of the foundations and the towers and the infrastructure, we get more output for that fixed foundation cost. So again, applications in the Great Plains states offshore. What are some of the potential issues, right? Probably the biggest issue is that if you look back at that resource map, you see that the wind power is a long way from the load, right? Windmills in Texas, in the Texas Panhandle, are a long way from Dallas. So it's a challenge in Texas to move that power from the Texas Panhandle to Dallas-Fort Worth, where the load is. Same way here, right? We have a lot of wind resources out in Iowa, but that electricity has to move from Iowa to Chicago, right? Again, that's one thing that the current president is trying to address with some of his infrastructure investments, right? Making improvements to the electrical grid to allow that power to move from where the renewable resources are, right? So we do have some localized impacts, visual noise, bird kills, right? I think there's still some controversy about bird kills from windmills. Certainly, I think the next thing that you'll see in the coming years is development of offshore wind resources in the United States. Again, I should take the question mark off of there, because now, again, I think in the last year or so, the government is moving towards allowing windmills offshore along the East Coast. Another renewable technology is geothermal. In this case, a little hard to see from this picture here, but in this case, when I say geothermal, I'm referring to a system where we tap the heat that's available beneath the Earth's surface. So this will be fairly localized where there are those resources available. So again, we're going to draw that heat out of the Earth and run a kind of conventional steam power plant. What's more common, maybe sometimes called geothermal, but I like to be more specific, is talk about it as a ground source heat pump. So in this case, we're using the constant temperature of the Earth as either heat source or heat sink for a heat pump, right? So this is the same kind of heat pump that you might have sitting outside of your house with an air source. But in this case, we are burying pipes in the ground, either horizontally if there's a large land area, or vertically if space is more constrained. So again, in the wintertime, we're taking heat out of the ground, and in the summertime, we are essentially taking cools out of the ground or rejecting heat to the ground. And this works because the ground is going to be at a relatively constant 50 or 55 degrees year round. So if we design our well field correctly, and if we have a good balance between winter and summer loads, then we have the ability to get both heating and cooling out of the ground. Right now, this is still not 100% renewable, right? It still takes some electricity to run the heat pump, but the heat source or heat sink makes this far more efficient than if this was an air source system. Certainly a good thing to point towards electrifying and decarbonizing. Right, here's a good little catchphrase here: 75% free environmental energy, right, plus 25% electricity equals 100% heating or cooling, right? So we're taking a heat source from the constant temperature of the Earth, running it through our mechanical cycle here, and using it to heat or cool. I'm not sure how many of you are familiar with the Unity Temple in Oak Park, right? The famous Frank Lloyd Wright designed building. We did I say we because I'm a member of the congregation there. We did a major renovation a few years back. So as part of that renovation, we put a geothermal system to heat and cool the temple. So I took some pictures. This was back in, I think it was the summer of 2015. We drilled a well field out in front of the building. Obviously, you don't see it now because those wells and the piping are below ground. But here you see the drill rig at work. Again, those of you who are familiar with Oak Park, here's the corner of the public library. So here's a drill rig out drilling the boreholes for the vertical geothermal. Yes, yeah, Bea, this work was permitted. Well, we did a couple of things. Obviously, the work was subject to a building permit, as any major construction project would be. We also did a test well, which I think is typical for a large geothermal installation. A few years earlier, we drilled another well on the property and made some measurements as to the characteristics of the soil, how well it would allow us to transfer heat. So the designers of that system used the data from the test well to design this particular system. So we had a pretty good idea, how much heating and cooling capacity we could get from each borehole. So you see here, again, here's the sidewalk blocked off with a construction fence. So this would be Lake Street and Kenilworth. But you see here's the top of the boreholes, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think we put 8 or 9 of them out there. Again, you don't see that now because all that piping got buried underground. But it's a fairly elaborate undertaking to get this large drill rig in to drill those, to drill the well and put concrete pipe in there to case it. But it's worked out fairly well for us in terms of the system that they were able to put in the church. So again, ground source heat pump, let's look at the pros and cons of the technology, right? So well drilling is fairly common, right? The people that do this in the machinery is fairly common. What's really required is a specialized design to know, how much performance that you're going to get out of each hole that you drill in the ground. Scale and price, again, this is field construction using standard materials. So, it's not something that's really going to scale up well. You're going to be drilling holes in the ground. So again, some good applications for ground source heat pumps, where we have similar heating and cooling requirements over the year is really something that's important. In the case of a commercial building like this one, we have to heat part of the year and air condition part of the year, and that works out well for a geothermal system. Again, another good application in this case was we didn't have a good place to put that, the cooling tower or the condensing unit that you would normally have to reject the heat from an air conditioning system. Obviously, potential issues is the ability to access the site for well drilling, right? Obviously, it's, in this case, we had the ability to use this front yard of the church and to get that equipment in there and do the boreholes. That is, may not be the case in a lot of homes and in other sites, right? We also have some embodied energy. A lot of steel got buried in the ground there. I think there were 8 or 9 holes, each, I think 300 feet. So 300 times 8 of 4 or 5 inch steel pipe. A lot of steel got buried in the ground. So this is really a long-term type project. And is it renewable energy? I would say yes, because again, it really helps support an electrification strategy. So again, here are my opinions. These are my opinions only. Other people who would analyze the situation might see things differently, but from my perspective, renewable energy, that's most likely to work. Certainly passive solar, correctly managing solar gain can be incorporated into almost any project, right? So if we look at, orientation and mass and where the windows are located and how they're protected with shading, we can have passive solar heating in almost any design. Certainly photovoltaic, it's going to work almost any place where you have good solar access, right? Again, not every house, not every site is oriented correctly. In my case, right, we have a nice south-facing roof with lots of area, but unfortunately our next door neighbor has a house that's taller than our house, so our roof is shaded. So not every house, not every building is going to be able to access PV, right? We do have now community solar available to us as an option, right? We can buy the output of photovoltaics that's generated off-site. The market is also bringing new financing options available. Certainly in the state of Illinois, with the energy legislation that was just passed recently, we have the we have a financing support that's being made available by the state. So again, ground source heat pump. If we have space for a well field, that's certainly a reliable, well-established technology, and that supports our move towards a green, all-electric future, right? If we're converting natural gas space heating to electric with renewables, that's moving us in the direction of decarbonization. Again, most likely to work, PV at the utility scale, close to parity. What does that mean? Close to parity means that, in the right locations, utility scale photovoltaics can generate electricity at a price in line with other conventional options. When I say conventional options, would be let's say a natural gas plant, right? We can build photovoltaic or wind. We can build those projects at about the same price as we can build fossil. So this is why we're seeing an increase in the installation of photovoltaics and wind, right? We're still not doing it fast enough. It's got to happen a lot faster, but we're at a point where the prices are lining up. So what are some of the challenges? Obviously, the electric grid is a major challenge, right? We have to move that electricity from generation to load. We have to be able to move the electricity from the Texas Panhandle to Dallas Fort Worth, from central and western Iowa to the loads in Minneapolis or Chicago, from windmills in Kansas, to loads in major cities, right? That's a challenge. Ditto for utility scale photovoltaics. Again, that electricity has to move from the place where the resource is to where the load is. The other challenge we have is we have to now balance supply and demand where we have a variable or intermittent resource, right? So, gone are the days where the coal-fired power plants can be running, full out all the time. Right now we have, the sun shining or not shining, and the wind blowing or not blowing, right? So that we have to learn how to balance that stuff out. And I think I showed this before, but this is a good example of the challenges of integrating renewables in the grid. This is again the duck curve from California, right? Somebody put this data together and they said, oh, that looks like a duck, right? So we see that during the midday we get more and more generation from solar in the state of California, and then what happens is that to the late afternoon and evening hours, when the sun starts to go down and loads start to pick up, all of a sudden we have this tremendous challenge that the utility has to ramp up their conventional generating resources to be able to continue to match supply and demand, right? So again, that's a challenge, and we'll have to figure out ways of meeting that. Large scale batteries and energy storage will certainly take care of some of that issue. So some takeaways, right? This is not something that's in the far off future. Viable renewable energy sources are here now. A lot of options exist both on site and off site, and at the utility scale. Again, at the level of an individual project, right, which still requires integrated design and careful analysis, right? If we're gonna get some performance out of our passive solar, we have to design the building shell correctly. We have to design well, and as always, efficiency comes first, right? So before we start talking about passive solar, we have to make sure that the walls are well insulated, the high performance building envelope, right? Efficient appliances and other things that are going to be heating and cooling loads. So again, if we're really serious about efficiency, we reduce the loads, and renewables can make a fairly substantial contribution. Okay, any questions? Okay, watching the time here, I'm going to shift gears here. We're going to kind of summarize. Here we go. Come on. We're going to bring this back to LEED strategies, right? I've spent the last, I don't know, 3 or 4 weeks talking about various topics related to energy and energy related technologies. We're going to bring it back to the LEED EA credit category, right? EA, energy and atmosphere. That's where that's where most of the points are, or a lot of the points are. And I showed this graph a couple weeks ago. Again, this one works a lot better if you see it live on the EIA website, because then you can click on things and the numbers pop out, and it's a lot easier to read than the screen capture I took. But again, buildings are 41% of U.S. energy consumption, right? So the work that we're about as construction professionals, right? We still have a fairly large slice of the pie that we have to figure out how to reduce. And again, we're getting better here, but still renewables are only 12% of our consumption, so we have a long way to go. Talked about this before, 50% reduction by 2030, net zero by 2050. These are the challenges that we have ahead of us, right? These are the things that you're going to see in your careers as construction professionals. Right, so getting back to LEED is a tool to measure building performance. Right, LEED helps us identify the right strategies that we should employ in our sustainable or green building design. Right, LEED helps answer the question of, what does green really mean? And in the LEED rating system, it's meant to address these 7 impact categories, but number 1 of that impact category, as I put in red there, is to reverse global climate change, right? So a lot of as we'll see when we look at the scorecard, a lot of stuff in LEED EA is related to energy and atmosphere, a lot of points there. Right, again, we looked at this before, early in the semester or middle of the semester. We looked at the LEED fundamentals, right? Credits are worth 1 point. Different credits are weighted differently. LEED values those strategies that reduce the impacts on climate change and those with the greatest benefit for indoor environmental quality, right? So again, climate change is important to us. The LEED rating system recognizes that and provides maybe a little hard to see on the slide here, right? But out of a 100-point scale, optimized energy performance is 18 possible points, right? So 20% of 100 points could come from energy and atmosphere, from improving energy performance, if not more. Right, here's O&M, right? So again, O&M focuses on operations, BD&C is on design, and again, even more points available in the optimized energy performance for E&A. So energy and atmosphere. So again, as I mentioned before, in one of my previous stops in my career, I worked with a big company, helping them do LEED certification of their existing properties, right, under the EB O&M, operations and maintenance, existing buildings. So, we picked our candidates, with sites that had fairly strong energy performance, good Energy Star scores, And if we had a good solid Energy Star score, then getting EBOM certification was certainly not a layup, but we had gone a long distance by that good energy performance. In the EA credit category, like there are in the other credit categories, there are some prerequisites. One of the prerequisites is commissioning. Sometimes you see commissioning, since commissioning is a long word to spell out, and I always have to look it up to make sure I don't spell it wrong, but oftentimes it's abbreviated with capital C, little x, or you might see it as RCX, retro commissioning. But essentially, commissioning is a systematic process of looking at all the building systems as they were installed and making sure that they are actually operating, that they were installed and operating in accordance to the OPR, or the owner's project requirements, right? To make sure that they are operating in accordance with the way that the building was designed, right? So commissioning is a structured process to make sure that the building is operating in accordance with what the designer's intentions were. And a CXA, a commissioning agent or commissioning authority, is the person or the team that does this work. Quite often, they will be independent from the design team because they are, kind of acting as a check and balance. So again, commissioning is a structured process. We're trying to, minimize or eliminate design flaws, construction defects, figure out, make sure everything's working the way that it was supposed to work, right? This is a human endeavor. It's construction. There's always errors and mistakes in construction, but the goal of commissioning is to find, identify, and correct those errors, so the performance that the designers had in their design and their energy model is actually realized in practice. Right. Another prerequisite for LEED EA is that we have to meet these minimum standards of energy performance, right? So again, in LEED, a prerequisite is something that you must do. So your building must meet the current energy standards. In this case, I think LEED is written around ASHRAE 90.1. So you have to meet that as a minimum. And then you get credits for going over and above. So you get credits for performances that is beyond 90.1, right? That's a can do. So prerequisite is a must do. Going beyond that is something that you can do. Rating systems typically have a baseline. So baseline means if you took that same design and constructed the building to meet the requirements of ASHRAE 90.1 or another energy code, how much energy would that building use? And then the rating system says, okay, you have to do better than that baseline building. And we've seen this young woman a couple times now looking up at the bar, right? So the rating system LEED is encouraging us to set the bar higher and drive towards better building performance, right? Now drive towards net zero, right? That's what we have to do here. Again, some definitions in LEED world. There'll be regulated energy. So some of the things that we can generally influence in a building, the lighting, the HVAC, the heating, ventilating, and air conditioning, the domestic water heating. Those are things that are called regulated energy, and that will typically be trying to minimize. Actually, we should be trying to minimize all these things, but we as designers may have less impact on the computers, the office equipment, the kitchen, the laundry, the elevators, the escalators, right? There's certain process things in the building that we may have less control of. So LEED recognizes that and says, okay, let's focus our efforts on the regulated energy, and we'll pay, not that we should pay no attention, but pay less attention to the process energy. Another prerequisite is metering, right? So the goal of metering here is to provide data that we can use for continuous improvement. So the old saying is you can't improve what you can't meter or what you can't measure, right? So the goal here is to be able to measure and use that data to drive continued ongoing improvements. Let me hit one or two more slides here and we'll take a break because my voice is starting to give out again. The other prerequisite, or one of the other prerequisites, is refrigerant management. Again, the refrigerants are those chemicals, they're the working fluids in refrigeration and air conditioning systems, right? We think of them maybe as Freon, right? Freon is a trade name from DuPont for their chlorofluorocarbons. But in the case of lead, we don't want the older chlorofluorocarbon-based refrigerants because those are linked to ozone depletion, right? We figured this out, I don't know, 15 or 20 years ago, where the CFCs were damaging the ozone layer. So we decided that, or we didn't decide that there was, legislation done on a global basis to phase out CFC-based refrigerants. So again, in lead world, we can't have any CFCs in our systems. Right. So again, this is something that I think the folks who figured this out got Nobel Prizes, but these long-lived CFC molecules made their way up into the upper atmosphere, and the sunlight, knocked a chlorine atom off of there and was destroying this ozone layer that's thin layer up in the upper atmosphere that shields us down on the Earth from UV radiation. So this was a good example of the agreement that nations reached to phase out CFCs was a good example of a successful example of nations getting together and solving a problem. It would be nice if we could do the same thing successfully with global warming. So why don't we take 10 minutes or so here? So we'll get back a couple minutes after 8. And in the meantime, while you folks are getting your stretch break in, I will go back and I think Mac, you said you had your presentation, so I will go download that and have it loaded up here. So we'll be back in 10.